Proactively going out and searching for threats in the network can feel pretty intimidating. It's easy to be overcome by the constant stream of noise, or falling down rabbit holes, or pulling on threads only to watch them unravel horribly in front of you. But really, we don't have a choice anymore. We have to assume that attackers are present in our networks and are actively looking for ways to access credentials and expand their influence. The latest M-Trends data from Mandiant makes that painfully clear. But it also points to some hopeful silver linings, particularly around dwell time. The earlier we can catch an attacker in their attack chain, the more opportunities we'll have to stop them before the intrusion escalates. And so in this video, I'll walk through a simple 3-step structured threat hunting process that you can apply right now in your own environment. My goal here is to give you a repeatable approach that helps you avoid wasting time and stay focused on finding meaningful signals of compromise. And then after that, we'll hop into a live example of using this very methodology to find evil. First off, what even is threat hunting? Well, everyone you ask is probably going to have slightly different answers, but we can think about how traditional cybersecurity strategies focus on reacting to attacks after the damage has been done. Threat hunting flips that approach on its head, and instead of waiting for an alert, threat hunters are going to start out with a hypothesis. Right? We have to ask ourselves, who is likely to target my organization? And where would they attempt to gain access from? And what tactics, techniques, and procedures, or TTPs, would they use? And ultimately, how would their activity appear in our environment? Right, so almost putting our own attacker's head on and thinking, if I were attacking my network, where would I start? Right, if I were trying to move laterally or pivot between systems within the network, what configurations would I take advantage of? What remote access tools might I use? And whose credentials might be up for grabs? Right, if I were trying to get domain dominance and take complete control over the network, who are the high privileged users that I might want to target? Right, what paths to domain administrator exist in the environment? The key is that threat hunting forces us to ask these questions up front and then go hunting for signs of that activity within our networks before the damage has been done. That kind of sounds difficult, doesn't it? That's because it is, right? It really is, but it becomes manageable if we have a structured process to guide our hunts. And so let's get into our first step. Now, that first step in our structured threat hunting process is to define a hypothesis. Right? We need to have some semblance of what we're trying to answer before we go off hunting. And so this is where we pause and ask ourselves, what are we actually looking for? Right? What is the attacker behavior we might believe is present in our environment? And so our goal here is to turn that question into a clear and focused statement, right? A hypothesis that we can then go out and test using our data. For example, we might hypothesize that an attacker's gained access to our network and is using something like psexec for lateral movement. Or maybe a malicious macro document has been used to launch PowerShell on a workstation. Whatever the case is, the key is that we're not blindly searching opportunistically, right? We're hunting with purpose. And once we have that hypothesis, our job becomes to search for proof, right? We want to either prove or disprove that this specific technique or behavior has occurred in our environment. And that's harder than it sounds, because our goal has to be tied to tangible indicators, right? Actual artifacts in the data that we can go hunting for. A broad hypothesis gives us direction, right? It's like our North Star to prevent us from veering off track. But it's not specific enough to guide our entire hunt. And so we need to break that broad idea down into smaller, more actionable pieces. Right? We need to ask what artifacts or entities or relationships between those entities would exist if this specific attack or technique has occurred. Right? What piece of evidence that, if we find it, will help us prove that the attack might have taken place? And so the idea is that we need to break our investigative questions down to the point where we can feel confident querying a single artifact source to find the answer. And so that might mean looking for a specific type of network connection, right? If there's an outgoing connection to a remote IP address, right? Or if there's lateral movement happening between systems. Maybe it's a file dropped on disk, right? Maybe there's something unique about that file, right? Like its size, or maybe even strings or indicators inside that we can match on. Maybe we need to look at process activity. Right? Are there specific process chains being launched? Winword.exe spawning PowerShell.exe, right? Something like that would immediately raise suspicion. Are there registry changes or additions that we can look for that might indicate persistence? And really, this step is just the beginning, right? You're not expected to know off the top of your head every single artifact or indicator tied to every single technique out there, right? That's where research and threat intelligence comes in. Right? So models like the MITRE ATT&CK framework are incredibly valuable at this stage. Right? They essentially give us a playbook, a way to map our hypothesis to known attacker techniques and expected artifacts so that we can then plan a focused and efficient hunt. Now, Step 2 in our structured threat hunting process is to define our evidence sources. Right? So at this stage, we need to ask ourselves, where can we actually find or acquire the evidence that will help us confirm or disprove our hypothesis? Now, depending on the tactics or techniques that we're focused on, the data sources we turn to can vary. Right? We might need to look at web server logs, right? Or Windows event logs, maybe sysmon logs if they're available. Right? Maybe we're turning to IDS telemetry or firewall logs, or even web proxy data. The key is to determine which source is most likely to contain the evidence that we're looking for. Right, the one that will give us the best shot at finding those indicators that's tied to whatever technique we suspect. Right? For example, if our hypothesis is focused on a phishing email, well, we'd probably want to examine mail transaction logs, right? Or maybe the received mail on our email gateway appliance. If we think the victim clicked on a malicious URL, well, getting our hands on something like the web proxy logs tied to that user could also help us prove that. Or if we believe that a file was downloaded as part of an attack, right? Like a piece of malware, well, we could look to EDR telemetry, or even Sysmon's file create stream hash events, right? That might show us that a file was downloaded. And we want to look at any related network connections or process executions around or tied to that file. Now, it's also important to think about which individual fields within these data sources will actually help us. Right? In that Sysmon file download scenario, we might want to capture the remote IP address, right? Or the domain name, which we can get from perhaps the zone.identifier alternate data stream, right? Or maybe correlating with DNS query logs. We'd want to see what process initiated that connection as well, right? And maybe what command line arguments it used. And again, the list goes on and on. The point is that defining your evidence sources isn't just about picking a log type. It's about understanding exactly what parts of that data will give you the clues that you need. Right? Because oftentimes these raw log sources can be normalized and abstracted to us by our tooling, which is nice, but it also has some cons, right? But if we understand the fundamental piece of data that we're looking for, we can cut all the way through that abstraction, right? And this helps us ask the right questions of our tools, right? And get to the data points that we actually need to help us prove or disprove that hypothesis. And ultimately, that's what keeps our hunting focused and efficient, right? And again, this will always depend on what specific behavior or specific technique we're looking for, right? And of course, the more experience you gain, the faster you'll be able to identify the most relevant sources and the most relevant fields for each hunt. Over time, you'll build up that muscle memory and this instinct that makes this step feel much more natural. Now, step 3 in our structured threat hunting process is all about transforming the data. The idea here is that we need to be able to work with and manipulate our data and telemetry in such a way that allows us to find evil, right? And this is where we take the evidence that we've gathered and actually interpret it and draw meaningful conclusions, right? It's one thing to collect logs and collect telemetry. It's another thing to format and analyze that data so we can find the signals that matter, right? An important point here, tools don't analyze anything, right? They physically can't. It's us, right? It's the analyst on the other end of that data that's actually analyzing it and drawing conclusions and supporting those conclusions, right? And using the evidence to tell a story. We have different ways in which we can transform and manipulate data. Sometimes this could be just as simple as performing a basic string match, right? Or maybe applying some regex to pull out known indicators. Other times we might need to look at statistics, right? For example, aggregating or stacking values, identifying the top or the most common entries, or flipping that around and focusing on the rarest or least frequently occurring data. For example, we can surface the least frequently occurring executables that were run across our environment. And an executable that shows up only 3 to 5 times out of maybe hundreds or thousands of systems, that's an anomaly, right? It's probably not part of the standard workstation image or application that everyone in the organization uses regularly, right? It could be completely benign, but it's our job to sort of tell that story. In other cases, we might want to visualize activity over time. Maybe we want to look at the duration of network connections or try to spot spikes in activity that don't normally align with our baseline network patterns. And that's really just the key here, right? We need to be able to select the right data sources, but we also need to know how to work with that data in certain ways that cut through the noise, right? We want to be able to surface things that are unusual, right? The outliers. And while finding an anomaly doesn't automatically tell us that we've discovered malicious activity, it does narrow the scope of our investigation, right? If we start out with 1,000 systems and now we're focused on just a handful that show rare or maybe anomalous behavior, well, we've made our hunt far more manageable and far more effective. And that's really the heart of this structured threat hunting methodology. And the beauty of this approach is that it's consistent and repeatable, right? No matter what you're hunting for, we start by defining a hypothesis so we know exactly what attacker behavior we're trying to uncover. We then identify the right evidence sources so we can actually find proof, right? Or disprove that behavior. And then we transform and analyze the data in ways that will help us spot the signals and surface the anomalies, right? And really zero in on the things that matter most. And so now let's take a look at this methodology and apply it in a live example so you can see exactly how it works in practice.
Elevate your cybersecurity expertise with TCM Security certifications. Our certifications offer in-depth practical training in penetration testing and ethical hacking. With real-world exam scenarios and expert guidance, you're not just gaining a certificate, you're gaining a skill set that's in high demand. Visit certifications.tcm-sec.com and take your first step towards a distinguished cybersecurity career.
And so step 1, I need to define a hypothesis, right? And so for our current focus, let's think about lateral movement, right? It's sort of the act of the attacker pivoting from one compromised host onto another within the environment. Now, lateral movement can show up in our telemetry in many different ways, right? But for this hunt, let's narrow it down and focus specifically on detecting PSExec activity. If we head over to MITRE ATT&CK and do a search for PSExec, we'll land on its software page that you can see here, where we can see all the various techniques that PSExec is associated with. Right, for example, it can remotely create accounts on target systems. Right, it can create or modify Windows services, or it can write. Right, it can write files to the admin $share. Right, among other capabilities that we can see here. And so our hypothesis might be something like, we believe an attacker's gained foothold into the environment and is attempting to move laterally between systems using PSExec. And from that, we can start to form investigative questions. Right, for example, do any hosts have evidence of PSExec execution? Right, or maybe similar tooling that enables remote service creation? But that's still a bit too broad. Right? We need to break that down into smaller targeted questions that we can actually go out and hunt for. Right, so we might ask, have any new services been created on systems in our environment that could indicate PSExec or similar lateral movement tools? Right? And we can answer this by looking at Windows service creation events, right? Like security ID 7045. Right? Or if we have sysmon, if we're collecting that, we can look at sysmon event ID 13 for registry value sets. Right? We can ask, have any binaries been written to the admin $share, right? Or other administrative shares? Because as we looked at, PSExec typically drops a service binary on the remote system to execute commands. Right? So we can hunt for this by looking for file creation events in those paths. Now, there's another reliable indicator, which is name pipes. And so when PSExec initiates a connection to a remote system, it sets up name pipes between the source and destination machines. Right, and these pipes act as the communication channels between PSExec clients and the service binary that gets dropped on the target. And so what makes this useful as an indicator for us is that these pipes typically follow a predictable naming convention, right, which means that they stand out in the telemetry. And so we can hunt for these using sysmon event IDs 17 and 18. And so you can start to see, by breaking it down like this, we can take what starts out as a complex high-level question. Is this malicious, right? Or is there lateral movement into my environment? And we can approach it piece by piece, right? We can hunt for specific artifacts in our data that give us real tangible evidence of what happened. And of course, there could be many other artifacts that we could, in theory, look for, right? We're really only scratching the surface here, but the idea is to keep this example focused so you can see how the methodology applies in practice. Now, I can go ahead and take my research a step farther here. In this case, because I know that I'm hunting for specific tool artifacts, I can try to understand how that tool is constructed, right? And what indicators it's programmed to leave behind. And so if we can understand a tool or a script that's being run, if we can take the time to break it down and reverse engineer it, we can often uncover the logic or conventions that it uses to name its various artifacts. Right? That could be service names that it creates, or file names that it drops, right? Or maybe scheduled tasks that it registers, or even registry keys that it modifies or creates. We might observe, for example, that a certain tool always generates a service name that's exactly 16 random letters long, right? Or that its DLLs always follow a particular naming convention. And so what we're looking at here is this serviceinstall.py file that's part of the Impacket toolkit. And this script is a helper module that's used internally by tools like PSExec or WMIExec and other scripts, basically to remotely install and configure and execute a service on the target system. Right, so this script handles the actual mechanics of uploading a service binary, right, and creating the corresponding service, and then performing some cleanup efforts afterwards. Specifically, if we look here under the service install class, we can find this little snippet here that basically tells us the whole story, right? It kind of reveals how Impacket generates the names for the service and the service binary. And so you can see we have service name and also binary service name. And we also have these random clauses that are being invoked specifically through the ASCII_letters method here, right? So under string.ASCII letters. And we can also see, if I can close that, we have various ranges, right? So in this case, we have 4 for the service name. And then if we go down to the binary service name, we have a range of 8, basically invoking the same kind of operations here. And so if we continue to reverse this and try to understand what's going on, basically if no service name is explicitly provided when the tools run, it's going to generate a 4-letter random alphanumeric string to serve as that service's name, right? Like ABCD. If no binary name is provided, it's going to do the same thing. This time it's going to generate a random 8-letter alphabetic string, and then it's going to append the .exe to that file. And that's extremely telling for us, right? As we're wanting to go out and hunt for these indicators, well, we now know how the recipe was made, right? Similarly, if we were to pull up the main psexec.py script as part of the Impacket toolkit here, we can search for 3 specific pipe names, right? So if I just do a Control F here for remcom, we'll eventually be able to find these 3 definitions here. Right, and these pipe names here are commonly associated with Impacket's psexec.py iteration, right? And so we have remcom standard out, remcom standard in, and remcom standard error. Right, and so you can see here that through these pipes, it allows for sort of this full duplex communication between the attacker and target, right, where we sort of get this command input and output that gets streamed in real time. And because we have sysmon logs in our telemetry, we can search for both event ID 17 and 18, which log the actual pipe creation and connection activity respectively. And so both of these indicators here are just beautiful for us to have as defenders or threat hunters. Right? We now know the logic that goes into naming these artifacts, and we can now turn them against the attacker. And so all we need to do now is just write the regex, right? We can write one pattern for those 4-letter service name strings, and we can write another pattern for those 8-character service binary names. And so, for example, if I were to search for the system event code of 7045, right, for those service creation events, but I also want to catch those suspicious 4-letter service names, well, I can use the regex command and provide a pattern just like this, where all we're really doing here is matching the A to Z in capital form and also the A to Z in lowercase, right, to match all those characters. And we're just repeating that 4 times, right, to get that range of 4 for those 4 letters. And then I'll just create a table with some of our most important fields here and run a search. And what do you know? We have a match, right? You can see under service name, that is in fact a 4-letter, seemingly randomly named service name. For the image path, we also have a 8-letter randomly named executable. Right, so already this is sort of getting the ears perked up that, hey, we might be dealing with some psexec activity here, right? Especially if we already had some indicators or suspicion on this host, for example. Now, again, speaking of the executable or the binary name, we can also run another search, again, for event code 7045. This time we can search for the image path and provide that same kind of pattern, this time grabbing an 8-range set of random characters with the .exe extension. And we have to sort of double backslash out all of our commands because we're using regex, and that's how Splunk in this case likes that to be done. And just like that, we're getting another match, this time for the exact same event, because this time we're looking for the image path field where we're matching it to seemingly the system root here, so C:/Windows, and then we have this randomly named executable. And so you can see that by truly understanding the technique and the software or the tool used, we can really reverse engineer and write these queries. Right? We can turn seemingly random patterns into more trivial detection for us. Right? These patterns are extremely easy for a human analyst to spot at a glance, right? But now with these queries, it's just as easy for us using the SIM to spot at machine speed. And so to wrap everything up, I can run a very simple search against our sysmon logs, specifically looking for those name pipes that begin with that remcom, right? So you can see here for pipe name as the field, I'm just placing in that remcom string, and then I'm surrounding that in wildcards just so I can match anything surrounding that, right? And again, that's going to be sysmon event ID of 17 for those pipe creations, and event ID 18 for those actual connections to those pipes. Then I'm just creating a table and sorting it based on time. Excellent. And so just like that, we can see that this process, again, this randomly named executable here, likely initiated these name pipes, right, which we can see through event ID 17. And we can see the names of these pipes are pretty indicative, sort of these hallmarks of Impacket's psexec execution. Right, we can see the remcom, and then we can see the communication, the standard out, standard error, standard input, and also these sort of random suffixes at the end of them as well. And shortly after, we can see that the system process with the process ID of 4 actually connects to these pipes, which we can sort of identify by the event ID of 18. And this is exactly how PSExec brokers its communication between the attacker and target. And so just like that, we turned what could have been some stealthy attacker infrastructure into reliable detection opportunities. Right? By understanding how the tool works internally, from its use of randomly named services and binaries, to its creation of predictable named pipes, we managed to flip the malware author's design choices here into their own weaknesses. And that's the power of using a structured threat hunting methodology. And by following these 3 simple steps, defining a clear hypothesis, identifying the right evidence sources, and then transforming and analyzing the data, we can stay focused. Right? We can cut through the noise and dramatically increase our chances of finding attacker activity before it escalates. And so I hope this video gave you a good practical starting point for building or improving your own hunts. And if you found it useful, consider leaving a like and subscribing if you haven't already for more content just like this. And let me know down in the comments which threat hunting scenarios you'd like to see covered next. So thanks again for watching and happy hunting.